Hello students, we will continue our presentation on the structural system of skyscrapers. We had begun last time by showing you the basic or the fundamental structures were used in skyscrapers when Chicago School happened. At that time they were using a simple steel frame which came to be known as the moment frame skyscraper, and this continued on with various other developments for which predominantly the structural engineer Fazlur Khan of Skidmore, Owings and Merrill was responsible, and he is credited to a very large part of the major development in skyscraper structures. We looked at the brace tube, we looked at the tube-in tube last time, and we will continue on from there. A very extraordinary skyscraper came up in New York in 1978, designed by Hugh Stubbins and Associates, called the Citicorp Center. I remember seeing this skyscraper when I was an undergraduate student, and I used to really marvel at the skyscraper, the way, the aesthetic of the skyscraper, but more than that we marvel at the structural technology used in this. It was at one time considered to be the most risky or dangerous skyscraper in New York because of its extraordinary building form, which came because of extraordinary circumstances. The reason was that on the site there was a church building, and they were not willing to let go of that building or allow it to be demolished. Then came a kind of arrangement between them, and that was that we will allow you to build this building provided that you will demolish the church and erect the church at exactly the same spot. But in order to do that, the building had to come up in a structural mechanism that would not impinge in any way on the church building. No column was supposed to pass through the church building. And the solution that was found was this, that the entire Citicorp building is standing on these 4 massive columns, not on the corners because that would then penetrate the church building here, but shifting it and putting 4 columns in the center of each side. The structural engineer William LeMessurier, who was responsible for this 59-story tower with 4 massive 35-meter high columns positioned in the center of each side, not at the corners, to accommodate for the church in the northwest corner, and the entire building is cantilevering 22 meters over this new church that was also erected after demolishing it. And then the mechanism was to have load bearing braces like this, as you can see here, these load bearing braces in the form of inverted chevrons, and the load transfer would take place from the floor plates to these diagonal braces, going down to from in this central spine like this and to the column and then to the ground below. So each chevron redirected the load to their center downward into the ground over this uniquely, through this uniquely positioned column. Another reason we find here, another quality that we find here is, this is the AT&T building that was designed by Philip Johnson, and this is the Citicorp Center, and both pinnacles you find are very unique identification of the two buildings. The reason is that at street level it is very difficult to be able to make out which skyscraper belongs to which corporation. All of them would look very much alike at street level unless there were some typical features, but generally from a distance, if they were able to see the pinnacle, it was very easy to identify both the AT&T building and the Citicorp Center because of this pinnacle, and this gave both these buildings what came to be a form of or a method of giving corporate identity to the building. One of the reasons why Citicorp Center had this pinnacle also is because it has got a TMU, a mass tuned damper that has been provided right at the top of the building, a TMD that has been provided here to prevent for lateral sway that happens because of either wind loading or in the case of a seismic event. Then came the idea of the bundle tube, again this was propagated or put forward by Fazlur Khan. When the height increases, one tube is not sufficient to be able to resist lateral loads from either earthquake or winds. Therefore, the method of bundle tube was found, in which the structural system consists of several tubes which are tied together to resist the lateral forces, and the building that came up as a result of this was called the Sears Tower, now it's known as the Willis Tower, by Skidmore, Owings and Merrill. Bruce Graham was working for Skidmore, Owings and Merrill, and this was corporate late modernism in a building where functionality was given the maximum importance. So this building basically has a floor plate, the base, which has got 9 squares in it, from which 9 tubes rise up. Each tube is 23 meters by 23 meters, and as they rise up, they are then bundled together at different heights, and there are staggered levels created as the building rises up. So all 9 tubes don't rise up to the full height being 442 meters or 110 stories, which is the tallest. At that time when it was built, Willis Tower was not only the tallest building in the US, it was also for some time the tallest building in the world. And this is how the towers are rising. So you find that all the towers are rising up to the 50th floor, then 2 towers stop rising, and then the remaining rise till the 66th, then up to the 90th, and then from 91 to 108, only 2 towers are continuing. The interior columns are placed at the perimeter of each of these 9 tubes, which are 23 by 23 meter, and these singular tubes are then bundled together in this multi-tubed structure, and then they are connected by these belt trusses to bind them together. So if we think of it in empirical terms, it's a very simple structural method of taking these tubes and then tying them together with these ties or these braces, and the floor sizes reduce by eliminating these 23 meter by 23 meter tubes as the whole building rises up. So at various levels you find different configuration of the building. Now this is not only it proved to be very economically efficient for very tall skyscrapers, but also it gave a very versatile formulation of the architectural space or the floor plate of the building. And as a result of this, now we didn't just have to have simple cuboids rising up to great heights, they could have varying shapes in the building, and the tube units were able to provide that various shapes, and they could be bundled in different groupings, and the buildings need not any longer be box like. So we have varying ones like the one Magnificent Mile by Skidmore, Owings and Merrill in Chicago in 1983, then the Trump Hotel and Tower in Chicago again by SOM in 2005, and of course the tallest building in the world today, the Burj Khalifa in Dubai, also by Skidmore, Owings and Merrill in 2010. These are all examples of bundled tubes. As you can see in the Burj Khalifa, there are these tubes that you see, and this is rising at varying heights, and then they are bundled together. The structural steel frame of this building, as in many other skyscrapers, was pre-assembled in different sections, brought to site and bolted in place on site. It was a very lightweight building skin having a black aluminium frame, and that was having bronze tinted glare resistant or glare reducing glass curtain wall, and thus the indoor temperatures could be much controlled. It minimized expansion and contraction of the frame, and this setback design was predominantly as a result of the space requirements proposed by the client, and thus turned out to be one of the most iconic skyscrapers the world had seen. Very large office floors have been provided for the company's day-to-day operations, but there are also lesser, smaller floor areas provided for tenancy of different forms, and smaller floors for tenants as per their requirement have lesser floor area. Now another system that came up after that for very tall buildings was the hybrid system, a system where the basic concept of the tube is used but is supplemented by other structural support. Used in super tall buildings that have got extreme loading, that face extreme loading, for example when a typhoon happens, and where the tube system cannot provide the adequate strength that is needed. So in the case of the One World Trade Center that came up on the site of the twin towers that were destroyed in the terrorist attack in 9/11, this One World Trade Center tower, rising to 541 meters, is today the tallest building in the US. It has a high strength concrete core, and it has got a perimeter steel moment frame on the outer periphery, and the so they are paired together for extra rigidity and structural redundancy. I might have mentioned to you last time also, redundancy happens in case a fallback arrangement is provided in the skyscraper. In case the main structural part of the skyscraper fails, there are other structural members, other structural parts within the building that will take over and prevent the building from collapsing. Now, high strength concrete and steel have been used in this building. It has been provided with tapered corners to provide for aerodynamic optimization and to reduce exposure to wind loads and reduce the amount of structural steel that would be required. Another thing is that the inner core and the perimeter steel frame are connected by these beams, and this is, like I told you last time, this helps in transferring some of the load of the core to the perimeter tube, and this also reduces the sway in the perimeter tube because of this additional gravitational load coming on it. Now, the floor plans show that there are high strength concrete walls that are provided at the core. And how thick are the core walls? They are 42 inches at the base and 30 inches at the top. This is the structural backbone of the tower, and this enhances the blast resistance and progressive collapse prevention in case of anything happening to the building. The core contains the elevators, the stairwell and the mechanical services. And besides that, there is an additional feature provided in the One World Trade Center because of the experience of the previous attack, and that is a blast protection wall has been provided. You see it here, and there are these two 56-meter high windowless concrete walls have been built at ground level to protect from truck bombs or other ground level attacks. But in order to maintain the aesthetic, because it is windowless, they have been provided with these prismatic glass panels to maintain or to retain the aesthetic of the building. Now, one more development that has happened lately in the 21st century is the coming up of super slender skyscrapers, and the reason is, what was the reason in earlier times also, that land in cities like Beijing, London and New York is becoming very scarce, and we need to build taller, as was the case then, but now land is even more scarce than what it was at that time, and as a result of this increasing shortage of land, there is a demand for this commercial space and more slender buildings, and these tall and slender skyscrapers are becoming increasingly popular also because now today we have the technology available to be able to erect them. They provide, or they require a very small footprint and are able to provide living and commercial space. Now, the design of any skyscraper is governed by the slenderness ratio, that is the height to width ratio of the building. In order for a tower that is having this height to width ratio of 7:1, this is by the New York building codes, if slenderness ratio is greater than 7:1, then it is considered as slender. But in the case of these super slender skyscrapers, the structure engineers are actually working with SRs which are greater than 10:1 or 12:1, and the most slender skyscraper of all, that has come up on 432 Park Avenue, is having a slenderness ratio of 15:1. This is that tower. That means if you take the side of the building, the height of the building is 15 times higher than one of its edges. And this is the tallest residential building in the world, or rather I should say the most slender residential building in the world. Now, the critical factor when we develop a super slender tall building is the stability and the selection of materials for the structural members. We cannot do it with steel because steel would vibrate like a tuning fork and would not have enough weight because of very high slenderness ratio. It would sway very much, and we need to increase the mass of the building. If the building slenderness ratio is smaller, if it is less than 7:1, then automatically the building mass is higher, and the building, even if made with a steel frame, will not have that much sway. The slender the building built with a steel frame, the sway will be much more. We have to increase the mass, try to put down the building, hold the building to the ground. In order to do that, we are primarily going to work with concrete as the primary structural material. Now, in this case of 432 Park Avenue, which is 425 meters tall, each story height is 4.75 meters. The total floor area of the building is in excess of 38,000 square meters, and the footprint of the building happens to be 28.5 into 28.5 meters, and the height is 15 times 28.5 meters. So, this is the outer perimeter of the building, outer perimeter tube. This is a bundle tube, and this is, or rather I should say, this is a tube in tube, and there is an outer perimeter tube, and then there is the tube of the core inside it. So, this tube in tube system has a 9 meter by 9 meter RCC core with high strength concrete and reinforcement, and the perimeter tube normally would be a steel moment frame in a tube in tube structure, but in this case it turns to be a concrete frame system. Now, the core wall is 75 centimeters thick to enhance the stiffness of the building. So, the outer tube frame connects to the central concrete core at every 12th floor with these large stiffening beams that you find at every 12th floor. These every 12th floor also coincides with the plant room. So, there is a plant room at every 12th floor. There are these stiffening beams at every 12th floor connecting the outer perimeter tube with the inner core. The plant rooms themselves are not glazed. They are not glazed, as you see here, they are not glazed, so that wind can pass through and through, and the wind induced sway can be reduced. If we have a complete structure and the wind strikes it, then the sway happens because of this building's resistance to the wind. If we were to thus puncture it, the wind would pass through and that sway would be reduced. That is why this thing has been applied here, and this is the concept of a blow through floor. That means the wind is allowed to pass through these every 12th floor. Not only that, 2 TMUs or tuned mass dampers are provided at the top of the building to control the building acceleration as a result of lateral sway or because of seismic action, but also to limit acceleration because the weight of the building is reduced, is a problem, and increases sway because the mass is less. 1,300 tons of extra weight has been loaded on top of the building to reduce the sway. So, that is an addition. But in spite of this, there have been issues concerning this building even till today, and there has been a controversy because of the sway of the building. You can read it up on YouTube. There are videos which are discussing the structure of this form and the difficulties that it has raised because of the sway, and also the corrective action which is being taken because there are other super slender towers that have come up in the vicinity of the same building. Another very interesting structural system, very innovative, was developed for the Hong Kong and Shanghai Banking Corporation, their headquarters in Hong Kong, designed by Norman Foster in 1986. At that time, this building turned out to be the most expensive skyscraper per square foot at that time. And this is a part of the high-tech movement which I will talk about in my later lectures. This is having a structural steel exoskeleton, a skeleton which is on the outside of the building. There are creatures like for humans, for example, we have an endoskeleton, our skeleton is within, but there are certain insects, for example, that have got the skeletal system outside their body, and that is called an exoskeleton. So, any building like HSBC which has got a structural system on the outside of its body, it is an exoskeleton. And here the entire building, the unique part of this building, which we will probably be seeing no detail later, was completely assembled on site the overall building, the various parts of the building were exported from different parts of the world. Like for example, we will discuss this later, the toilet unit was completely erected in Tokyo and then shipped on site and then installed on site. We will look at those aspects of high-tech architecture later. So the structural solution turned out to be that there would be these coat hangers, like a coat hanger, and there would be these floors, certain number of floors, which would be hanging from the coat hangers. The coat hanger is connected to this mast. There are 8 such masts, 4 on one side and 4 on the rear of the building, and from this coat hanger is the mast, and from the mast are hanging these certain number of floors. So they hang by these coat hangers through these 8 massive masts, and the consequence of that is that at the plaza level, the ground level of the building, there is no column support intervening in the plaza. It is completely a through and through space, and has turned out to be a very vibrant socio-cultural space of Hong Kong. You have these escalators that are going up to the main banking area, which is starting from above the plaza. So this is the larger picture of the coat hanger and the mast. These are the 8 masts that have been in the front and the rear of the building, and the steel exoskeleton is fireproof with ceramic fiber insulated blanket, and then it is covered on the outside by aluminium to give it a very smooth metallic finish. This is showing you the aluminium covering on the outside, and this is a part of what we will study later as high-tech aesthetic. One more unique way of putting together a tall building was devised by Frank Lloyd Wright, and he, as we will be talking about in my later lectures on Frank Lloyd Wright, he was very fascinated by the cantilever. He used it in Falling Water, one of the most famous houses of the 20th century, and many other projects. So he also came up with the idea of a skyscraper in which the floors are cantilevered, and the concept was based on that of a tree. Just as we have a tree and all its branches are cantilevered, thus we have a building with a central trunk and the floors are cantilevering out from there. So we have the Price Tower in Bartlesville in Oklahoma, in which each floor is cantilevered. And so the difference between the two concepts, both around the same time, we have the Seagram building, which became the very summa of what a steel building in the 20th century would be, the gridiron skeleton moment frame by Mies van der Rohe, and parallelly about the same time came the Price Tower. Did not really take on, it did not become very popular as a structural frame. In fact, I do not think anybody else beyond Wright was really there who used the cantilever floors in their skyscrapers or the tall buildings. This moment frame was the one that succeeded. Again, Wright used another tall structure. Now again, please understand that there is not a single very tall building where even Wright experimented with making the floor cantilever floors, but the second tall building that came up was the tower of the Johnson Wax Corporation, a Johnson Wax building that came up earlier actually. Price Tower was a residential building that had come later. This was built earlier in the 1940s as a part of the larger complex. This was where he had brought in this concept of a tree, and these are the branches that are springing out from the central trunk, and these are how, when the construction is taking place, you can see these cantilevered floors. So much so, this very deep foundation was provided, just as a tree would have deep roots, and the trunk would rise from there and the branches cantilever out. Now here what they did was, this company was manufacturing Pyrex tubes, and Wright used those Pyrex tubes in this building. As you see here, these Pyrex tubes are wrapping the building, and because the floors are cantilevered from the central trunk, there is no column as an outer support on any side. This is all curtain wall Pyrex tube wrapped around the building. So much so he has even taken it at a higher fascinating level, in that each alternate floor is actually circular, it is just about touching the Pyrex tube, and it is as if floating, because it is also cantilevered from the trunk. Now, what do we perceive will happen in the future? What is the next generation of skyscraper structure? We have looked at the moment frame, the brace tube, the tube-in tube, the bundle tube, the hybrid tube, the exoskeleton, the cantilevered structure. The next generation actually is the mega frame. One of the buildings that is coming up based on the concept of the mega frame is the Jeddah Tower. Now, Jeddah Tower is very similar in its structural mega frame as the Burj Khalifa. The Burj Khalifa was based on the mega frame, but also it was a bundle tube concept. Here in the Jeddah Tower, it is a large scale framing system which is a stiff outer shell, reducing the need for internal columns. In the Jeddah Tower, there is this core. This is a hexagonal core. It is a hexagonal core, not a regular hexagon, but a hexagon, and it is provided by these, it is buttressed from three sides by these Y-shaped members. These Y-shaped members are buttressing this core from the three sides and thus supporting it and giving it extreme height stability. Then there are these mega columns which rise from the extremities, and this enhances the seismic and wind resistance of this building so that it can be built to a mega tall height, and it will have a lot of interior flexibility because the interior columns have been reduced to a very large degree. Now, this kind of structural form, the other thing that are being tried out, for example, is the exoskeleton. Now, we have seen the exoskeleton in the HSBC building. Now, here the structural elements are placed outside the Citicorp Tower in Beijing. This is designed by Kohn Pedersen Fox, and there are this bracing that has been provided on the outside. This is the it's an exoskeleton digrade form that has been provided, and this is able to handle the lateral loads, increases structural efficiency, and allows for column free interiors within the building. Another development that is happening is the development of adaptive and dynamic structures. The buildings that change shape and stiffness in response to external forces like wind and earthquake. An example is the El Bahar Towers, which uses a dynamic shading facade, but this is primarily meant for energy efficiency and endothermal comfort. In the time to come, this same idea in future designs may extend this to structural elements. So, this is an indicator of what might come in the future. So, currently this kind of facade increases energy efficiency and provides resilience against climate change and gives good endothermal comfort. Other methods that are being tried, for example, are suction based wind damping. Instead of heavy mass tuned dampers being used in the building, negative pressure zones are being created to counteract the sway because of wind. For example, in the Ping and Finance building, which does not have a bulky tuned mass damper, there are lighter skyscrapers that use lesser material and improve the occupant comfort. Other concepts that are coming up in the future are, or that are being worked on, are 3D printed structural components, a suction foundation in which the foundation, there is vacuum pressure to anchor the skyscraper without the need for deep excavation, particularly useful for mega tall skyscrapers. And then we have self-healing concrete, which is made using bacteria or nanomaterials embedded in it that helps in repairing cracks. An example of that is, for example, the Lotte World Tower in Seoul. In the future, skyscraper will integrate AI optimized design. They will have more and more of carbon neutral materials, and we will have kinetic structures to improve energy efficiency and thermal comfort, and these will be the what we perceive, what we imagine is what in the near future we will be having in our buildings. Technology will be able to push efficiency beyond the current limits that we have, even structurally. Now, just to give you at the end of our 6 presentations on the study of skyscrapers, types of skyscrapers we studied. We studied, for example, ideas like the privately operated public spaces. We looked at the idea of zonal regulations, particularly in the city of New York, which was foundational to the way skyscrapers evolved over time. So let's go back again to New York and see how skyscrapers evolved there. We have the Flatiron building in 1902, the Equitable building which resulted in the 1916 zonal regulation or bylaws in 1915. We have the Empire State building that came up as a result of the zonal regulation, the tallest building at that time in the world in 1931. Seagram building, which is the summa, the very epitome of what a glass and steel wood building would be in the 20th century heading into the 21st. The World Trade Center, which unfortunately became a landmark which reminds us of a tragedy, and then we have the One World Trade Center which has come up to show the resilience of the human spirit in 2014 at the same spot of the earlier World Trade Center in 2014. Thank you so much. We have wrapped up our series, 6 presentations on skyscrapers, and now we will continue onwards to study individual great masters like Frank Lloyd Wright, Le Corbusier, Mies van der Rohe and Walter Gropius, and we will move on from there. Thank you.